Hey, yo. Ever wonder what's really going on inside those wires? We're about to take a deep dive into the electrifying world of, well, electricity. Got some cool notes and diagrams right here, ready to break it all down.
It's amazing how something, well, so fundamental to our lives can seem so mysterious, right?
Yeah.
Let's try to shed some light on it. What do you think?
Let's do it. First things first, we got to talk about these things called charged particles. They're like the VIPs of the electrical world.
Yeah, that's right. Imagine these incredibly tiny particles, even smaller than atoms, zipping around with a sort of invisible uh, force field around them. That force field is what we call charge.
Okay, so they're tiny, but they're mighty, and they come in two flavors, right? Positive and negative.
Right.
Like the universe's tiniest game of magnets, with opposites attracting and likes repelling.
Exactly. And it's this attraction and repulsion that creates that electrical push that makes everything work. Speaking of which, that push has a name, voltage.
Voltage. Okay, is that like the driving force behind electricity?
It is. Think of voltage as the difference in electrical potential energy between 2 points. The bigger the difference, the higher the voltage, and the stronger that push or the steeper that hill those charged particles want to roll down, so to speak.
Okay, so the higher the voltage, the more those charged particles want to move. But how do we actually get them moving? That's where the flow of electricity comes in, right?
You got it. That flow is what we call electrical current. It's like a river of charged particles, all moving in the same direction. We measure current in amperes, or amps for short.
Amps, volts. It's like we're learning a whole new language.
We are, but trust me, it's a language worth learning because it helps us understand the world in a whole new way.
I'm all for learning new languages.
Yeah.
So we've got these charged particles, we've got voltage pushing them, and we've got current, which is their flow. But something tells me there's got to be some, resistance along the way, right?
You're way ahead of me. Resistance is a huge factor in how electricity works. It's the opposition to the flow of current. Like, imagine trying to run through a crowded room versus an empty one. It's much harder to move when there's a lot of resistance.
Oh, okay. So resistance is like the traffic jam of the electrical world.
A perfect analogy.
Hmm.
And just like in traffic, resistance can slow things down. It's measured in ohms, named after the brilliant physicist Georg Ohm, who figured out the relationship between voltage, current, and resistance.
Okay, hold on a second. Relationship. Are we talking about some kind of electrical love triangle here?
Huh? I guess you could say that. It's more of a fundamental law of physics than a love triangle, but it's just as powerful, right? It's called Ohm's law, and it basically states that the current flowing through a conductor is directly proportional to the voltage across it and inversely proportional to the resistance.
Okay, that sounds a little intimidating. Can we, break that down a bit?
Absolutely. Imagine a water hose. The voltage is like the water pressure. The current is the amount of water flowing through the hose, and the resistance is like how narrow the hose is. The higher the pressure, the more water flows. But if you use a really narrow hose, it restricts the flow, even if the pressure is high.
Okay, that makes a lot more sense. So Ohm's law is like the ultimate equation for understanding how electricity behaves.
Exactly. It's a cornerstone of electrical engineering, and it helps us predict and control how electricity flows in everything from tiny microchips to massive power grids. But to really appreciate the magic of Ohm's law, we need to dive deeper into the world of electrical circuits. You ready?
Circuits, like what we have in our homes and gadgets. Now that's a topic I'm really curious about.
And that's where things get even more interesting. Think of a circuit like a pathway or a loop that guides those charged particles, allowing them to flow in a controlled way.
So it's like the electrical equivalent of a highway system,
Yeah.
with different routes and destinations for the current to follow.
Precisely. And just like on a highway system, we need specific components to direct traffic and keep everything running smoothly. That's where things like conductors and insulators come in.
Okay, conductors. Those are the materials that electricity loves to flow through, right?
You got it. Conductors are like the superhighways of the electrical world. They have a unique atomic structure that allows those charged particles to move through them with ease. Think of metals like copper and aluminum.
Ah, that's why we use copper wiring in our homes. It's an electron superhighway.
Precisely. And on the flip side, we have insulators, the materials that electricity has a much harder time flowing through. They're like the roadblocks or detours on our electrical highway.
Insulators. Those are important too, right? Wouldn't want electricity flowing everywhere it's not supposed to.
Exactly. Insulators are crucial for safety and for making sure the current follows the intended path. Think of the rubber or plastic coating around electrical cords. That's insulation, protecting you from getting shocked.
It's like the electrical equivalent of wearing rubber gloves when working with something dangerous.
Another great analogy. And, speaking of how electricity behaves in different materials, we have to talk about static electricity. It's a phenomenon we've all experienced, and it's a great example of how charged particles can build up on a surface.
You mean like that shocking zap you get when you touch a doorknob after walking across a carpet on a dry day? Tell me there's more to it than just bad luck.
There certainly is. That zap is the result of a buildup of static electricity caused by the transfer of charged particles, specifically electrons, from one surface to another.
So those little electrons are hitching a ride on our shoes as we walk across the carpet, and then they all jump ship when we touch something metal. It's like an electron exodus.
That's a great way to put it. And understanding how those electrons get transferred is key to understanding static electricity. There are actually two main ways to charge an object: by contact and by induction.
Okay, so charging by contact, that's like when you rub a balloon on your head and it magically sticks to the wall. You're transferring those sneaky electrons from your hair to the balloon, giving it a static charge.
You got it. It's a direct transfer of charge, like sharing a secret handshake with a bunch of electrons. But charging by induction, well, that's a bit more subtle. Imagine holding a charged object near a neutral object without actually touching them.
Okay, I'm picturing it. What happens next? Does the neutral object suddenly develop a craving for balloons, too?
Not quite. But the charged object does influence the neutral object from a distance. It's like it has an invisible force field that causes the charges within the neutral object to separate.
So it's like the charged object is whispering to the electrons in the neutral object, hey, come over here, the party's over here.
That's a fantastic way to visualize it. And this separation of charges, even without direct contact, is what we call charging by induction.
Wow, electricity is full of surprises. But all this talk about charged particles and their movements makes me think about something else. What are the different ways that electricity actually flows?
You're thinking about the different types of electrical current? We've got two main players here: direct current, or DC, and alternating current, AC. They both involve the flow of charged particles, but they have very different personalities.
Okay, so DC and AC like the power adapters for some of my gadgets, but what makes them so different?
Okay, so think of DC like a river flowing steadily in one direction. The current flows consistently from the positive terminal to the negative terminal. Batteries are a great example of a DC source.
So DC is like a one-way street for electrons.
Exactly. It's reliable and predictable, which is why we use it in things like batteries, electronics, and even electric vehicles. Now, AC is a bit more adventurous. Imagine a river that keeps changing its direction of flow, back and forth multiple times per second.
Whoa, that's a wild river.
It is. That's AC for you. The current alternates direction periodically, and it's the type of current that powers most of our homes and businesses.
Interesting. But if AC is so adventurous, why is it the one we use for something as important as powering our homes? Wouldn't DC be more stable and, reliable?
That's a great question. While DC has its advantages, AC really shines when it comes to long-distance transmission of electricity. You see, AC can easily be transformed, meaning we can increase or decrease the voltage as needed.
Transformed. Like Optimus Prime, but for electricity.
Huh. You're getting good at this. It's not quite as dramatic as a transforming robot, but it's still pretty cool. We use devices called transformers to increase the voltage for long-distance transmission.
Okay. Why do we need to, crank up the voltage for long distances? Wouldn't that make it more dangerous?
It all comes down to efficiency. Higher voltage means less energy loss as the electricity travels through those long power lines. It's like sending a package across the country via express delivery versus regular mail.
So AC's ability to be easily transformed makes it the winner for powering our homes.
Exactly. We can send high voltage AC over long distances with minimal energy loss, then use transformers to step down the voltage to a safer level before it reaches our homes. It's a brilliant system that makes modern life possible.
Wow, AC is like the electrical equivalent of a cross-country road trip. Efficient, adaptable, and always up for an adventure. But all this talk about voltage and long distances makes me wonder, what are some of the challenges that engineers face when it comes to transmitting electricity over those vast distances? What are the things that can, go wrong?
You've hit on a critical aspect of electrical engineering: power loss during transmission. Remember how we talked about resistance? Even the best conductors, like copper and aluminum, have some resistance, which means that some energy is lost as heat as electricity flows through them.
So it's like friction, slowing things down, and generating heat, even in those electron superhighways.
Precisely. And this energy loss, often referred to as line loss, is a major challenge for power companies. The longer the distance, the greater the potential for energy loss.
So it's like a race against resistance. The farther the electricity travels, the more energy it loses along the way.
Exactly. And this is where those transformers we talked about earlier really come into play. By boosting the voltage to very high levels, we can minimize the amount of current flowing through the lines. And since energy loss is proportional to the square of the current, even a small reduction in current can significantly reduce energy loss.
So it's a delicate balancing act. Crank up the voltage to reduce current and minimize energy loss, but also make sure it's safe for us to use in our homes.
Precisely. It's a testament to the ingenuity of electrical engineers that they've been able to create such a complex and interconnected system that delivers electricity to our homes and businesses reliably and efficiently.
It's mind-blowing to think about all the intricate processes happening behind the scenes, every time we flip a switch or plug in a device.
It really is. And we've only just scratched the surface of this electrifying world.
Right.
But even understanding these basic principles can change the way you look at things.
Absolutely. I know I'll never look at a light bulb the same way again. Speaking of which, it occurs to me that we've been talking a lot about the big picture of electricity, the power grids, the long-distance transmission. But what about the smaller scale? How does electricity actually work in something like, say, a simple circuit?
Excellent question. Let's break down a basic circuit. Imagine a battery, a light bulb, and some wires connecting them. Simple enough, right?
So far, so good.
Okay.
Got my battery, got my bulb. Let's get this party started.
All right. Now, inside that battery, we have a chemical reaction happening that creates a difference in electrical potential energy. Remember, that's voltage.
Right, like a little engine inside the battery, setting the stage for the electrons to flow.
Exactly. Now, when you connect the wires, creating a closed loop or circuit, those electrons, compelled by that voltage, start flowing from the negative terminal of the battery through the wires to the positive terminal.
So it's like a tiny racetrack for those electrons. But what happens when they get to the light bulb? Does it slow them down?
The light bulb is where things get really interesting. You see, the filament inside the bulb, usually made of tungsten, has a much higher resistance compared to the wires.
Uh-huh. So it's like hitting a patch of rough road on that electron racetrack.
A very apt analogy. And because of that higher resistance in the filament, the electrons have to squeeze through a bit tighter, causing friction and generating heat.
Okay, so the filament heats up, but what makes it light up?
This is where it gets really cool. That heat from the resistance is so intense that it causes the filament to glow, producing light.
Wow. So that simple light bulb is a testament to the power of resistance.
Precisely. It's a beautiful demonstration of how we can harness the principles of electricity to create something so useful.
It's amazing how something so fundamental to our lives can seem so simple on the surface, but is actually incredibly complex and fascinating once you delve into it.
It is, and that's the beauty of science and exploration. The more we learn, the more we realize how much more there is to discover.
Absolutely. This deep dive has been an incredible journey. I feel like I've gained a whole new appreciation for the invisible forces that power our world. Any final thoughts before we wrap things up?
Just this. Next time you flip a switch, take a moment to think about those tiny charged particles racing through wires, encountering resistance, and ultimately making our modern lives possible. That's a pretty remarkable thing.
Couldn't agree more. It's been a truly electrifying conversation. To our listeners, thanks for joining us on this deep dive into the world of electricity.